Let's consider the Big Bang beginning of the universe. And it's all undergirded by Einstein's general relativity. And here's a beautiful equation that denotes some of the features of that, incorporating tensor calculus. That's a lot more complicated than that looks. But his theory of gravity in 1917 predicted a universe in a state of acceleration or expansion, along with the curvature of space that occurs from mass. We've discussed that already. Now, Einstein was not too happy with the results of his amazing equations because he preferred an infinite static universe, which was the paradigm of the time, and his equations instead predicted something else. And that was cause for much consternation for him. Well, what did he do about that? He adjusted his equations to match his idea. He put in a cosmological constant to keep the expansion from occurring. Kind of a gravitational a force to oppose gravity, an anti-gravitational force. But then, shortly thereafter, as we've already encountered, Hubble discovered the galaxy distance recession velocity relationship. So recession velocity versus distance, that there's a relationship there. So the Hubble law relates the galaxy distance and recession velocity. The connection is simply that the more distant the galaxy is, the greater the redshift. The greater the redshift, the greater the speed that it recedes from us, and its constant is about 71 kilometers per second per megaparsec. This undergirds empirically the idea of the Big Bang, because as you reverse time, you get to the point of beginning where all the galaxies were together. So this is kind of a starting point for the concept of the Big Bang, beginning of the universe. Let's consider some very broad and key features of the Big Bang beginning of the universe. We have evidence for distant galaxies that emerged a billion years after the beginning itself. So when the universe was about 1 billion years old, we have the Hubble Ultra Deep Field, and we can visualize them, take images. Objects much beyond this, they're not emitting light that we can see. The first light of the universe that was produced in the universe was trapped for 380,000 years from the origin before it was released. I'm going to go into considerable more detail on that. Before that time, that 380,000 years, we have to rely on mathematical models to tell us what's going on and then make tests to see if the tests validate the theories. Now, if we reverse the cosmic clock, all the galaxies come together at a time in the past corresponding to the Hubble time, as I alluded to and we'll look at next also, about 13.7 billion years ago. It's not just the matter of the universe that was compressed to this one point, but it's space itself. Space unfurled and was expanded from that singularity. All compressed to that singularity at this single location, quote unquote, and as we've discussed, that location is really everywhere, not at some particular place. So the Big Bang occurred everywhere. Considering that, we should see the effects of the Big Bang, any way that we can detect it, any tools we have at our disposal to determine what's going on in the universe should reveal the same effects everywhere, since it occurred everywhere. So that's a really key point. Now, because of look-back time, the Big Bang can be seen basically now. It takes a certain amount of time for light to travel. It corresponds to the look-back time. And based on how long ago that was, we should be able to look back that far in light travel time and see the beginning. Now, basic physics tells us that the universe as a whole, as it expands, it cools. So very broadly speaking, we have temperature and we have seconds since the Big Bang. This is a highly logarithmic scale, very nonlinear, but we see it goes from very hot, very early, cooling off as time goes on. So that's a very broad look at considerations for the Big Bang. How can we use the Hubble law and the Hubble constant to determine the age of the universe? Well, it's really pretty nifty. We have this expansion rate that's based on the recession velocity of the galaxies. The recession velocity is the Hubble constant times the distance. We've encountered that already. Now let's assume for the moment that the universe expands and always has at a constant rate throughout time. Then the time since the Big Bang, how much time has taken place since the universe started expanding till now, is simply time is distance over velocity. It's the separation distance divided by the recession velocity, which is d over vr. That's just basic kinematic description of motion. However, notice that the Hubble constant is recession velocity over distance. Comes out of this here. Hubble is recession velocity over distance. Now, what's the relationship between these two things? Oh, recession velocity over distance is the opposite, the inverse of distance over recession velocity. So, the time for the universe to expand to its current size is then simply the inverse of the Hubble constant. So the time since the Big Bang is 1 over the Hubble constant. That's really an amazingly useful and beautiful relationship. You can maybe now see why the Hubble constant is such a desirable thing, and it's very important to get it right as well. If we convert the units properly, kilometers per second per megaparsec, which is what the Hubble constant is usually expressed in, converted to units corrected for the amount of years for this expression gives us 13.7 billion years approximately since the Big Bang. So that's the time that the expansion has been occurring. Now during that time, the universe has been expanding, space has been expanding. The implications of that are that the materials, including photons in that space, is expanded along with the space. The look-back time toward the beginning is directly related to the redshift. We interpreted that in the past as being a Doppler shift due to its motion. So, as we look at the Doppler shift, we get a recession velocity and all. That's based on, as we understand it, something moving through space away from us or toward us. But more correctly, it's a cosmological redshift due to the expansion of space itself. The photons are actually being stretched out rather than rapidly moving through the space. So that's how we want to consider this cosmological expansion. If you were a little bit confused on that cosmological redshift discussion, let me clear it up for you. So here's a picture of a photon being emitted by a galaxy, emitting a short wavelength photon toward our galaxy from here over to ours. And as we progress down in this direction, notice the grid spacing getting larger, smaller, bigger, bigger, biggest. So as time progresses, as that photon moves along, the grid spacing representing space is being expanded and stretched. So you notice that in each of these graphics, we have a little bit more than a couple grid widths corresponding to this photon. So by the time we get down here, it's been redshifted quite a bit because there's been enough time where space has stretched enough and it's stretched the photon with it. The misconception is that it's not a Doppler shift from a galaxy moving through space in the conventional sense. The galaxies are essentially not moving in the space they're in, so they don't have emission redshifts. But as the space is stretched, the matter is carried along with it, and the photons are stretched along with the space as well. So the redshifts are not corresponding to radial velocities away from us, even though it appears that way. The galaxies have apparent recessional velocities. So here's another picture. Don't want to emphasize or reinforce the incorrect picture, but that's what this is. Normal motion through space. Here we have Earth, and here's a galaxy moving away, and so you can imagine it's emitting photons in all directions. The ones toward Earth are redshifted, so that's the conventional way to think about it. And then that photon travels along on its way through constant normal space, arriving redshifted at Earth as we would contemplate it. So again, that's not the correct picture. The correct picture is the idea of the cosmological stretching of space itself. So we have a galaxy, sitting there in space, emitting photons in all directions. And as those photons are emitted, it takes a long time to travel to the Earth, and in that time, they are stretched out with the stretching of space. So the galaxy is not moving. It's the fabric of space that's stretching, and the photon gets stretched along with it. So hopefully that makes this idea of cosmological redshift understandable. A key feature of understanding the early universe is the way in which the fundamental forces themselves behave. And it all goes under the term the unification of the fundamental forces. And as I said, this is at the very, very beginning of time itself. It's that point right after the beginning where temperatures and conditions were so extreme that the fundamental forces of nature could actually merge into one. Now there are four known forces. There's gravity and electromagnetism, which are long-range forces, inverse squared type of forces that have no bound on the extent over which they reach. And then there's the strong and weak forces that are very short-range forces. Now the electromagnetic force, for instance, is a trillion times stronger than gravity. That's 10 to the 36 times stronger than gravity. However, it doesn't manifest itself so extremely in this sense because the number of electrons and protons in the universe are equal. Charges cancel each other, so the manifestation of this force is limited. Gravity is the only force that's boundless in extent. It has no limit on its range, and it's always attractive, so it ends up dominating the universe. The galaxies, the stars, planets, all this are controlled by gravity more than anything else, even though gravity is a very weak force in comparison. So this graph shows the temperature of the universe at the early stages and the time after the Big Bang. So we're very incomprehensibly small times, incomprehensibly large temperatures at which the various forces are understood to have merged. And in the merging, the unification, they act as one. So there's different phases that this goes through. Each one is very important. So just in brief here, we're considering this. We have the strong and weak forces. They act over the scale of nuclei, 10 to the minus 15 meters. Very, very small. The strong force holds together the nuclei. For instance, fusion happens, right? Remember, fusion is a process where the strong force grabs a hold of the nuclei to fuse them together because it can overpower the electromagnetic force. It's about 100 times stronger. The weak force is involved in the nuclei transformation, like radioactivity. So in the early universe, the forces become identical, force unification. And in fact, prior to 10 to the minus 35th seconds, we have the unification of these three forces, the strong, electromagnetic, and weak. They were all as one at that point. Now the conditions, the theory that is associated with describing the conditions of the universe at that point go under what's called grand unified theories or gut theories. And prior to 10 to the minus 43 seconds, we have the theory of everything, the TOE theories, which is also considered the Planck era. It's that point where all the forces, including gravity, are assumed to unify. All the forces in nature that are manifested distinctly now existed as one then. And it's also an era, this Planck time, where quantum mechanics becomes extremely important. And unfortunately, the effects of quantum mechanics and the predictions of general relativity are divergent, so we just don't understand the nature of reality prior to this time. It requires a theory of quantum gravity, which we don't have. So, nevertheless, we can investigate the very earliest moments of the universe, theoretically nothing before this Planck time, but close to the very beginning through particle accelerators like CERN, producing high energy collisions that replicate these conditions of the very early universe so we can get a handle on what was going on at the very earliest of time. So let's look at a short video regarding that and some other key early universe features that we'll investigate subsequently.
universe came into existence 13.7 billion years ago with the event known as the Big Bang. We have been able to see back close to the beginning, using telescopes to capture distant light emitted billions of years ago. The famous Hubble Space Telescope has allowed us to look back when galaxies were still in the process of forming. The WMAP provided us with an amazing view of the cosmic microwave background, the afterglow from the Big Bang. Before this point, the universe was too hot and light was unable to shine through the dense fog of charged particles. This prevents telescopes from being able to see beyond this point. However, there is a way to recreate the conditions of this early universe right here on Earth. The conditions of the early universe were of extreme heat and energy, which led to the creation of strange forms of matter and physics. For decades, particle physicists have been recreating these early conditions with particle accelerators, smashing particles together to create similar levels of heat and energy. Particle detectors are then employed to capture these events to help us learn more about what the universe was like in these early times. ATLAS is such a detector at the Large Hadron Collider. Late in 2009, the LHC and the ATLAS detector broke world records by creating and detecting the highest energy collisions ever made. In the years to come, it will reach its full capacity and push to even higher energies and further back in time. ATLAS will be discovering new kinds of particles, such as the Higgs, and unlocking new realms of physics that may include new dimensions of space and particles of dark matter. This frontier of knowledge will continue to be pushed to help us learn more about the origins of our universe and what happened a fraction of a second after the Big Bang.
So, taking a little broader view on the scale of time and temperature, we have this Planck era, which is still a realm that remains uncertain, the point where gravity separates out, following which we have the inflationary epoch here at about 10 to the minus 35th, 10 to the minus 36 seconds to 10 to the minus 32 seconds, when the strong force freezes out. So here's the strong force and it separates out. And then going on in time, this is very logarithmic, we have the weak and electromagnetic forces separating out. So this whole realm here, very short amount of time, is the realm of the unification and separation of forces, for that matter. And many other additional key events take place as we move along in time. So this is just giving you a brief overview. We have the confinement of quarks, basically the origination of the stuff making up the nuclei, the protons, the neutrons. Helium synthesis, ultimately the universe becomes transparent to photons. That's about 380,000 years after the Big Bang. And then the last part, really most of the universe in terms of time, is from here to here. And everything else that takes place up to galaxy formation and planets and ultimately people. Now, of course, since we don't know anything about the universe in the Planck era, prior to the Planck era, at 10 to the minus 43 seconds, it's certainly true that we don't know where the universe ultimately came from. And that's a very provocative question, and one that's speculated upon, sometimes at will, but something that seems consistent, an idea that's consistent with what we do know, is that perhaps at the very earliest stages, the universe was in a condition of non-zero energy, and it went from a transition from a false to a true vacuum, and in the process of which, kind of viewing this as rolling down into the true vacuum, associated with a energy transition that gives it a huge burst to literally accelerate the universe and expand it in a hyper manner, known as the inflationary epoch, shown here, where you see distance, scale, and time. In this very short inflationary time, we have a hyper expansion rate, a tremendous burst of expansion, not even limited by the speed of light, since nothing's traveling that fast, but it's the expansion of space. So this is a suggested, hypothesized view of the early stages of the universe, although there is some substantial evidence for this inflationary epoch, which is a key feature of our understanding of the Big Bang universe and answers a lot of questions that would otherwise be very thorny issues. So after this inflationary epoch, the expansion rate progresses at a more leisurely rate right up to the current time. Not quite this simple, but in brief form, this is kind of the picture of the early universe to the present time. There are many different visualizations that show this whole sequence from the very beginning of time, as we know it, up to the very present, up to the present time. And just wanted to give you one particular overview of this visually, where we have the Planck era, and then the grand unified theory era up to 10 to the minus 35 seconds, where the strong nuclear force freezes out, followed by the electromagnetic and weak force era, the particle era, the era of nucleosynthesis, which is only at 3 minutes now, then the era of nuclei, atoms, galaxies, right up to the present time, and key events associated with these different eras. So even though the first 3 minutes is just a tiny proportion of cosmic history, certainly not shown in proportion here, there's an incredible amount of things that take place in that short amount of time. Even the very first second, the very first thousandth of a second, there's so much that takes place. So next we're going to just investigate some of these early events in a little more detail as we try and get a grip on what's taking place all the way through the history of the development of our universe.